Well, welcome to this online revision session for AQA FP2. In this session we'll be covering the June 2010 question 6, which covers the topic of series and proof by induction. Well, you can see this question comes in two parts. The first part of this question is an algebraic show that, so you start with the left hand side and simplify it to obtain the right hand side. And then the chances are this part of the question will then be used, since the answer has been given, in the second part of the question, where we are asked to prove this summation is equal to 1 minus 2 to the power of n plus 1 over n plus 2 factorial by proof by induction. Okay, so first part of this question, I'm going to start with the left hand side and show that it reduces to the right hand side. So we can see on the left hand side we've got 1 over k plus 2 factorial minus k plus 1 over k plus 3 factorial. Now we've got to combine these two fractions together, so we need a common denominator. And the key thing for you to realise is that, just as with 5 factorial and 6 factorial, to get from 5 factorial to 6 factorial you just have to multiply by 6. So to get from k plus 2 factorial to k plus 3 factorial, we just need to multiply the top and the bottom of this first term by k plus 3. So if we do that, we will have k plus 3 over k plus 3 factorial, and of course the second term is already over k plus 3 factorial. And so now we can subtract one fraction from the other. So k plus 3 minus k plus 1 is just going to give you 2 over k plus 3 factorial. And that gives us our first two marks, a method mark for realising what we've got to do to get the common denominator there, and then the mark for getting the correct result out from there. Into the next part then, we're into the proof by induction. You remember proof by induction comes in two parts. The first part is where you put in the first value of n to show that the starting value of this statement is true. And then the second part is where you let n equals some value k, which we assume to be true, and then from that show that the value of k plus 1 must also then be true. And then by induction you have the necessary reasoning to show the whole thing is in fact a correct statement. In this case, for all positive integers n, so the first positive integer is 1. So if we let n equal 1 as our starting value, then we can see that this left-hand term here becomes 1 times 2 to the power of 1 over 1 plus 2 factorial. So this term is equal to 2 over 3 factorial, which is 2 over 6, which is just 1/3. And similarly then, if we take the right hand side, which is 1 minus 2 to the power of 1 plus 1, so it's 2 to the power of 2 over, again, n is 1, so this becomes 3 factorial. So this is 4 over 6, which is the same as 2 over 3, and 1 minus 2 over 3 is also 1/3. So both sides of this equation give you the same result of 1/3. So this is true for n equals 1. So that's good news. At least it's true for the first value. Okay, so now we move on to the part where we assume true for n equals k. In other words, what we are saying is that the sum from r equals 1 to k of r times 2 to the r over r plus 2 factorial is equal to 1 minus 2 to the k plus 1, because remember we've set n as being equal to k, over k plus 2 factorial. So that's the statement that we're assuming is true. Now we're going to let n equal k plus 1. And we're going to try and show that the statement is also therefore true for n equals this value. So now we're doing the summation from r equals 1 up to k plus 1 of r times 2 to the r over r plus 2 factorial. Okay, so we're now summing with that extra term. So what we need to do is to rewrite the sum from 1 to k plus 1 as the sum from 1 to k plus the additional term that has to be added on to that. And the additional term is when we substitute k plus 1 in for r. So that becomes k plus 1, that's the r, times 2 to the k plus 1 over, and then that now becomes k plus 1 plus 2, so this becomes k plus 3 factorial. Okay, well, what do we know about this sum from 1 to k? Well, we assumed that it was true that it was equal to 1 minus this term here, the statement in this line above. So we can put that in here, so it becomes 1 minus 2 to the k plus 1 over k plus 2 factorial, and then we got the extra term still being added onto the end there, so this is k plus, well, that was k plus 1 in there, wasn't it? Missed that out. K plus 1 times 2 to the k plus 1 over k plus 3 factorial. Okay, well, we know we have to reduce this again to 1 minus something, where the value of n is going to become k plus 1. So these two fractions that we have here, we need to simplify. Well, we can see that there is a common denominator here of 2 to the k plus 1, which will come out. And then what is left is the negative of what we were just showing. It's up in the red box, part A. This is what we showed in the first part of the question. So we can use this result to simplify this fraction here. And so this will become 1 minus, and so the 2 to the k plus 1 is the common factor. And what we end up with in here is going to be 2 over k plus 3 factorial. Okay, so where are we up to now from there? Well, that is now going to give us what we require, because you can see that what happens on the top when we multiply 2 to the k plus 1 by 2, that will become 2 to the k plus 2. So this becomes 2 to the k plus 2 over k plus 3 factorial. In other words, it's true for n equals k plus 1. Only thing is, just check carefully that this is in the right form when you compare it back with what you were trying to prove. If you put k plus 1 in for n, we get 2 to the k plus 1 plus 1, which is the 2 to the k plus 2, and we get k plus 1 plus 2 factorial, which gives us the k plus 3 factorial. Okay, well, there are 6 marks for this part of the question. So again, clearly we must have a method mark for being able to split this piece up and finding the correct terms in here. What else have we got? Taking out this factor and realizing and simplifying at this point here will be a method mark. Obtaining this correct form here and the answer part here, there will be an answer mark for that. Showing it's true for n equals 1, there'd be a mark for that one, showing that clearly. This part here, when I gave a method mark, there would also be an accuracy mark there for having the correct forms of each of the fractions in there. And finally, there would be 1 mark for setting out the method of induction properly so that it is fully explained. And remember, I've run out of space here, but you should write a final line explaining why you're applying, or how the method of proof by induction is being applied. Okay, two clear statements are the fact it's true for when n equals 1, assuming it's true for n equals k, we've shown that it's true then for n equals k plus 1. So by induction, the original statement is true for all positive integers. Well, if you found that solution helpful, there is more support for your revision if you go to the Further Maths Support Programme website for additional help.